Hey guys, welcome back. In this video, I want to prove this very interesting statement, which is derivative of e raised to x is equal to e raised to x. Usually, when we take the derivative of the function, for example, y equals to f of x. And if we take the derivative, y equals to f dash of x, usually the appearance of the function changes. But in this case, if we take y equals to e raised to x, then if we take the derivative of this function, it will not change. It will remain as e raised to x only. In earlier video, I've already told about the nature of the e. This e is irrational as well as transcendental number, which means we cannot express this e as solution to any of the algebraic equation. And this e is also called the Euler's number, and its value is 2.71 something. Now what happens is, as I have already told in the earlier video, taking the derivative of the function means we are finding the slope of the function at the point. For example, here, this graph is y equals to e raised to x. And if we take this derivative, then we are finding the expression of the slope of the function. But for this expression, it is observed that the curve of the derivative and the function itself is same, which means if we draw the curve of the function after finding its derivative, it will lie exactly same on this line. Okay? And this is very interesting result. That's why I have selected this topic today. Now what happens is, see, at this point, if we take the slope of this line at this point where x equals to 1, then our slope will be equals to e raised to 1. And if we take here x equals to 2, then our slope will be e raised to 2. And if we take here, then our slope will be e raised to 4 like that. Okay? Let us now start proving this from the first principle. And the first principle means the ultimate definition of the derivative. As we have already learned that, for example, if you want to find the derivative y equals to f of x, then from the first principle, the derivative of the function y is equals to f of x plus h minus f of x divided by h when h tends to 0. This is the definition of derivative from the first principle. By using this, let's prove that derivative of the function e raised to x is itself like e raised to x. Okay? Now from this function, let's plug in that y equals to e raised to x, okay, which means that derivative of the y is e raised to x plus h minus e raised to x divided by h when h approaches to 0. And now we can write this expression as from the exponential rule, that if we have like a raised to b plus c, then we can write this in the product form as a raised to b times a raised to c. Okay, so we can write this in this form: e raised to x times e raised to h minus e raised to x divided by h limit h tends to 0. Okay, now from here what we observe is this x is independent of the limit, because this limit applies only to this h variable, therefore we can isolate this e raised to x because it is independent of the limit. So by isolating this, we will now get e raised to x limit h tends to 0, e raised to h minus 1 by h. Okay. Now, as we have discussed in earlier video that there are two important results of the limit which surrounds around this e, transcendental number. That is, if we have something like 1 plus 1 over n whole raised to n, and when n approaches to infinity, then it will result in this number e. Or if we have something like limit m approaches to 0 of 1 plus m whole raised to 1 over m, then it will be e. So by using any of this expression and modifying this expression, we'll try to evaluate the limit and find the derivative of the function of which is e raised to x. Now we will have that let k equals to e raised to h minus 1, right? Which applies e raised to h equals to k plus 1 and h equals to ln k plus 1, right? Now with this, we will evaluate the limit also. See here, when k approaches to 0, what happens here? H also approaches to, when it is approaches to 0, it will be ln 1. So ln 1 is 0, so h will also approach to 0. So with this, we will modify this function and we will get dy upon dx equals to e raised to x limit k approaches to 0, and here this one e raised to h minus 1 is k divided by this h. This h here is ln k plus 1, right? Now we can further modify this by dividing both sides with 1 by k to reduce to any of this form, right? This form. So what we will do is, we'll divide like this: dy upon dx equal to e raised to x limit of k approaches to 0 1 over k times k divided by 1 over k ln k plus 1. Okay, now which will be e raised to x 1 upon ln k plus 1 whole raised to 1 over k limit when k approaches to 0. Why is because, see here it is logarithmic form, and we already know that if we have ln a ln b like this, then we can write in this form ln a raised to b. So here this is this form and I have written in this form. Now from this, since this k applies only to this expression inside, we can shift this limit inside. So by doing this, we can reduce this expression exactly to this form right here, this form. Therefore we can reduce this limit to e. So what we will have is, finally we'll have dy upon dx equals to e raised to x limit of k approaches to 0 1 over ln k plus 1 when k approaches to 0 1 over k. So this whole value is just e. So we will have, which will be equals to e raised to x then 1 over ln e, and this value, this ln e is equal to 1. So we will have e raised to x 1 upon 1, which is e raised to x. So with this, we have proved that this y is e raised to x, right? So we will have differentiation of e raised to x with respect to x will be e raised to x itself. So by using the definition of integration, we will also have integral of e raised to x dx will be what? E raised to x plus c. So this is another interesting and powerful result. So as I have already explained that in this curve of y equals to e raised to x, the derivative lies at the same curve and the slope at any value of x will be e raised to x. So corresponding to the value of x, the slope will differ. I hope that you might have enjoyed this proof, and I will see you in next video. Thank you for watching.